this module, you will learn about the shapes and energies of atomic orbitals. We have already learned that in quantum mechanics, all the properties of a system are expressed in terms of a wave function. This is obtained by solving the Schrödinger's equation. The wave function, psi, is a mathematical function that represents amplitude of the wave. It does not carry any physical significance. Therefore, the square of the amplitude of electron wave, that is, psi square, gives the probability of finding the electron at a point within an atom. This is predicted by German physicist Max Born. That is why the function psi square is called probability density and is always positive. By finding the probability density at different points in an atom, one can predict the region of space around the nucleus, within which the probability of finding the electron is the maximum. This three-dimensional space around the nucleus, where the probability of finding the electron is maximum, is called orbital. The probability of finding an electron is a function of distance r from the nucleus. The probability of finding an electron at a distance from the nucleus is called radial probability distribution. Let us look at the plots corresponding to the orbital wave function psi as a function of distance of an electron from the nucleus, that is, r, for the 1s and 2s orbitals. Similarly, look at the curves of probability density psi square as a function of radius for these orbitals. The following are the important conclusions that can be drawn from these plots. At r equals 0 or infinity, that is, at the nucleus or at infinite distance from the nucleus, the probability of finding an electron is 0. The peak of the curve indicates that the probability of finding the electron at this distance is maximum. For s orbitals, the number of peaks obtained in the plots is equal to the n value. Hence, for 1s and 2s orbitals, the number of peaks obtained are 1 and 2 respectively. For 1s orbital, the probability density is found to be the maximum in the vicinity of the nucleus and decreases sharply as the distance from the nucleus increases. On the contrary, for 2s orbital, the probability density first decreases sharply to 0 and then increases to reach a small maxima before it drops again to 0 with the increasing value of the radius. The region where the probability density function reduces to 0 is called radial nodes or nodal surfaces or nodes. For s orbitals, the number of radial nodes increases with the value of the principal quantum number n, and found to be equal to n-1. Therefore, 1s orbital does not show any nodes, whereas 2s and 3s orbitals show 1 and 2 nodes respectively. Probability density of electrons can be depicted with the help of the charge cloud concept or charge cloud diagrams. In this, the cloud of negative charge is represented by means of dots. Note that a dot represents the location of the electron at a given point of time. The cloud of negative charge is denser in certain parts than others. This indicates that the probability of finding the electron is maximum in that region. On the other hand, the probability of finding an electron in a particular direction or angle is called angular probability distribution. The probability of finding an electron in a particular direction or angle can be depicted by boundary surface diagrams. The boundary is drawn where the probability density remains fairly constant. The region inside the boundary surface depicts the orbital where the probability of finding an electron is maximum. That is, about 90%. The boundary surface diagrams define the shapes of various orbitals. Therefore, the shape of the electron cloud density and that of boundary surface determines the shape of the orbital. The boundary surface diagram for s orbital is always a sphere centered on the nucleus, irrespective of the principal shell to which the orbital belongs. This is because, for a given value of radius, the probability of finding the electron in the s orbital of a principal shell is found to be identical in all directions. Therefore, the shape of s orbital is a symmetric sphere. Note that, although all s orbitals are symmetrically spherical, the shapes of the s orbital belonging to different principal shells differ in two aspects. 1. The number of nodes, and 2. Size and energy. As the size and energy of the principal shells increases with increase in the value of n, their orbitals also follow the same trend. For example, the size and energy of 4s is greater than 3s, followed by 2s, and then 1s. Let us now discuss the shape and orientation of p orbitals. The boundary surface diagram for the p orbital indicates the presence of two lobes that lie on either side of the plane that passes through the nucleus, giving a dumbbell shape to the p orbital. The shape suggests that the probability of finding the p electrons is the maximum within the two lobes. The probability density function is 0 on the plane where the two lobes touch each other. Since the azimuthal quantum number L is equal to 1 for p orbital, the magnetic quantum number ML has values -1, 0, and +1, which represent three different orientations for p orbitals along the three axes, x, y, and z respectively. Hence, there are three p orbitals which lie perpendicular to each other. Irrespective of the direction at which the electron density lies, the size, shape, and energy of these three orbitals belonging to the same principal shell is identical. However, like s orbitals, the size and energy of p orbitals increases with increase in the principal quantum number. For example, the size and energy of 5p is greater than 4p, which in turn is greater than 3p, followed by 2p as shown. The number of radial nodes for p orbitals is given by the expression n-2. Therefore, number of radial nodes is 0 for 2p orbital, 1 for 3p orbital, 2 for 4p orbital, and so on. In addition to these radial nodes, for np and nd orbitals, the probability density function is also 0 at planes passing through the nucleus. These planes are called nodal planes. Number of nodal planes for a p orbital is 1. That is, the plane which passes through the origin at which electron probability of finding an electron is 0 is called a nodal plane. For example, the nodal plane for py orbital lies along xz plane. Nodal plane is also called angular node, and number of angular nodes for a p orbital is equal to the value of azimuthal quantum number L. For the d orbital, the azimuthal quantum number L is equal to 2. Therefore, the number of possible orientations given by the magnetic quantum number ml is 5, corresponding to ml is equal to -2, -1, 0, +1, +2. The boundary surface diagrams pertaining to these orientations, designated as dxy, dyz, dxz, dx square minus y square, and dz square, are shown. Note the similarity in shapes of the first 4 d orbitals, which are different from the fifth orbital, dz square. The shape of dz square is donut shape. All the 5 d orbitals belonging to a principal shell have the same energies. The size and energies increase with increase in the principal quantum number. For example, the order of the size and energy of various d orbitals is 5d greater than 4d, which in turn is greater than 3d. The number of radial nodes for d orbitals is given by the expression n-3. Therefore, the number of radial nodes is 0 for 3d orbital, 1 for 4d orbital, and so on. On the other hand, the number of angular nodes is equal to the value of L, that is 2. Hence, 2 angular nodes exist for a d orbital. For example, for dxz orbital, there are 2 nodal planes passing through the origin and bisecting the xz plane containing y-axis. Note that the total number of nodes for an orbital is given by the expression n-1. The total number of nodes is equal to sum of angular nodes given by L and radial nodes given by n-L-1 respectively. For example, let us calculate the total number of nodes for 3D, which is given by the expression n-1. As the value of n is equal to 3, by substituting the value of n in this expression, we get the total number of nodes 2. The value of L for d orbital is 2, and hence the numbers of angular nodes are 2 for 3D. As the value of n is equal to 3, the number of radial nodes as per the formula is equal to 0. Let's now have a detailed look at the energies of orbitals. As stated earlier, in general, the energy of the orbitals increases with the principal quantum number, and the energies of all the orbitals belonging to a subshell remains the same in the ground state. For single electron systems, such as hydrogen and other isoelectronic species, such as unipositive helium ion and dipositive lithium ion, the energies of all the orbitals for a given value of n are the same, irrespective of their subshell in which it is present, S, P, D, or F. That is, the energy of an electron exclusively depends on principal quantum number and not on azimuthal quantum number. For example, the energy of an electron present in 3s, 3p, or 3d remains the same, irrespective of it having different values of azimuthal quantum number. 1s in the hydrogen atom represents the most stable state for the sole electron and is called the ground state. The energy states with n greater than 1 represent the excited states for the electron in the hydrogen atom. Unlike the single electron species, the energy of an electron in a multi-electron atom depends on azimuthal quantum number, also in addition to principal quantum number. This essentially means that for a given value of n, the orbitals s, p, d, f possess different energies for different azimuthal quantum numbers. Let us look at the energy level diagrams for hydrogen atom and multi-electron atom, which depicts the arrangement of various orbitals. Now, let us understand why in case of a multi-electron atom, the energies of different orbitals of a given principal shell possess different energies in contrary to hydrogen atom. In a multi-electron atom, the different energies of different orbitals of a given principal shell is attributed to the inter-electronic repulsions among the electrons present. On the other hand, in hydrogen atom, due to the presence of only one electron, the only electrical interaction present is the electrostatic forces of attraction between the nucleus and the electron. Hence, in hydrogen atom, the subshells belonging to the same principal shell have same energy. Despite these repulsive interactions, the multi-electron atoms are as stable as the hydrogen atom, because the net attractive interactions between these electrons and the nucleus are more than the repulsive interactions among the electrons. The attractive interactions of an electron increases with increase in positive charge on the nucleus. The complete attractive interactions of the positive charge are not experienced by the outermost electrons, as the electrons in the inner shells tend to shield the electrons in the outer shells from positive attraction of nucleus. Thus, the net positive charge experienced by the outermost electrons from the nucleus is called effective nuclear charge, and the shielding of outermost electrons from the attractive forces of nucleus by the inner shell electrons is called shielding effect or screening effect. Despite of the shielding effect, the net attractive force experienced by the outer shell electrons increases with increase in nuclear charge. In other words, the energy of interaction between nucleus and electron, that is, orbital energy, decreases or becomes more negative with increase in atomic number. The energies of the orbitals in the same subshell decrease with increase in the atomic number or effective nuclear charge. For example, energy of 2s orbital of hydrogen atom is greater than that of 2s orbital of helium, and that of helium is greater than that of lithium, and so on. That is, E2s H greater than E2s He greater than E2s Li. The attractive and repulsive interactions in a multi-electron atom depend upon the shape of the orbital and shell. As the shape of s orbital is spherical, it shields the electrons more effectively as compared to p or d orbitals present in the same shell. In addition, due to spherical shape, the electron in the s orbital spends more time closer to the nucleus in comparison to p orbital. Similarly, the electrons in the p orbital spend more time closer to the nucleus in comparison to d orbital. This is due to the difference in the shape of their orbitals. Since the shape of the orbitals is defined by azimuthal quantum number L, we can say that the effective nuclear charge experienced by the orbital decreases with increase in the value of L. Therefore, s orbital with L equal to 0 is more tightly bound to the nucleus as compared to p orbital with L equal to 1 and d orbital with L equal to 2. Due to the difference in the net effective nuclear charge experienced by different orbitals of a principal shell, the degeneracy is lost and hence they show different energies. Because the effective nuclear charge experienced by the orbitals decreases with increase in L, the energy of s orbital is lower than that of p orbital, and that of p orbital is lesser than d orbital, and so on. With the increase in shell number n, the energy of the orbitals also increases. As a generic guideline, the lower the value of n plus L for an orbital, the lower is its energy. This explains why 4s possess lesser energy than the 3d orbital. If two orbitals have the same value of n plus L, for example, 2p and 3s orbitals, the orbital with lower value of n, that is 2p, will have the lower energy. You have now reached the end of this module. In this module, you have learnt that the shape of an orbital is depicted by its probability density function. The region where the probability density function reduces to zero is called nodes. The total number of nodes for an orbital can be given by the generic expression n-1. Probability density of electrons can be depicted through boundary surface diagrams, in which case the shape of the diagram gives the shape of the orbital. The shape of s orbital is symmetric spherical with only one possible orientation. The shape of p orbitals is dumbbell with three possible orientations along the three axes. 4 out of 5 d orbitals have the same shape but different orientations. The fifth orbital has a different shape and orientation. For single electron atoms like hydrogen, the energies of all the orbitals in a shell is the same, and the size and energy of orbitals increase with increase in the value of n. The subshells belonging to a principal shell of multi-electron species have different energies owing to the mutual repulsion among the electrons present in these subshells. S orbitals have lower energies than p orbitals that in turn have lower energies than d orbitals. The energies of the orbitals in the same subshell decrease with increase in the atomic number. The lower the value of n plus L for an orbital, the lower is its energy. If two orbitals have the same value of n plus L, the orbital with lower value of n will have the lower energy.